Okay, here we are again. I have got the MC12 driver circuit, pulse width modulation variable duty cycle circuit, a little cheap circuit with a op amp and 555 timer drives this coil. And in the center of the coil is my pint-size electrolyzer. And we are generating gas, but not at the rate that I really feel is good. It certainly isn't good enough, and it certainly isn't as prolific as I think Stan Meyer's apparatus is. Maybe it never will be. It's just maybe the nature of the apparatus. But I am generating, as you can see here, I am generating some gas, but it's not very much. And I've got about a 10-volt swing across those pair of wires, the plates, if you will, of the electrolyzer. There's about 10 volts across there, and I can drop it down and don't see much difference in the production, which doesn't surprise me a bit, since we should have around 2 volts around each of those, across each of those cells. But this is a parallel cell operation, so it's probably a lot different than your typical dry cell configuration would be. But we're generating gas, but not at a very good rate. Now, the frequency at which we're doing this is still the 7800 hertz. And I'm going to swing around to the scope and show you the waveform that's on the scope. I've also managed to eliminate, with a little fiddling around and playing around with the voltages on the MC12, I've managed to eliminate the 50 ohm load going going across the coil, I should say. And that seems to have helped some, but there's some characteristics of that MOSFET that I don't think are coupled well with the coil, and we're wasting a lot of power in that resistor. So it was good to eliminate it, but I don't think we're really getting the drive across there that we need. The scope may tell some of you a bigger story than it tells me. We do have nice spikes at the edges. Right now the duty cycle of the MC12A driver circuit is very narrow, and you can see it roughly in the scope between the spaces between the positive and negative spikes. That's basically the gap between those positive and negative spikes is the pulse width in one direction. The rest of it is the other direction. So it's not nearly a 50% duty cycle now. It's a much narrower duty cycle than that. But it seems to be the voltages and what have you of that MC12 circuit, the MOSFET of it, seem to be very specific, and I shouldn't say that, it's very touchy to get it to oscillate. So I'm going to swing around to the scope now, and let me zoom out here so we won't be too crazy. I guess what I'll do first is I'm going to zoom back in on that schematic and show you there's the output section of it, which is the MOSFET transistor with a clamp diode on the positive rail to protect it, and then it's driven by a push-pull configuration bipolar pair of transistors there. So I've looked at the gate of that MOSFET when it doesn't seem to be giving any output, and the gate of the MOSFET has the proper signal across it. It's got the full power supply rails in a nice solid square wave, not rounded corner square wave going to that gate. But the MOSFET itself does not seem to be switching with that signal unless there's the right load characteristics. Maybe it's an impedance thing. The DC resistance of the coil, as I've wound it, is about 70 ohms. 50 ohm resistor is better than a 300 ohm resistor or a 1K resistor in terms of how much signal it seems to get to the load, if I just measure it right across that load resistor, for example. But as I go lower in resistance, the lowest I've been able to go is about 25 ohms, which is much lower than the DC resistance of that coil. But it gets stronger. The voltage across that resistance gets higher the lower in resistance I go. Very counterintuitive. I also have another problem I'm fighting, which is the power supply I'm using to drive the MC12 is a pretty cheap power supply. It's a dual rail power supply that I fabricated probably 20 years ago. And when I start loading it up over about 1 amp or so, maybe a little more than 1 amp, the voltage starts to go down. So I do have the meter across, and so I'm monitoring the supply rails on the circuit, and it's sitting about 30 volts on the supply rails of that driver circuit. Alright, so now that you've seen the circuit, let me pan up here to the scope. And hopefully it'll focus in there. And you can see the nice spikes of the output waveform right across the coil. Well, actually, it's right across the electrolyzer output is what that is. And I measure it's sitting on the 2 volt per division scale right now. So I've got roughly 6 divisions, so 12 volts or so is going right across that that electrolyzer, which is a lot for the design. But as I say, as you saw before, we are generating some gas. It's just not very proficient. I hooked the 30 volt power supply up to it directly and cranked it, and it's about the same. It's really about the same production as what DC voltage would be across that electrolyzer design. So it may just be a limitation of that, basically a single plate design wound through there. But so that may be what we'll have to focus on is changing the electrolyzer design to be more efficient. And from what I can see, which is, it's so little gas, I really can't tell for sure, but from what I can see, having it in the middle of the Vortex coil doesn't seem to be having an effect on it. And it may be because it's not operating at the efficiency it needs to, and that may be why it's not being influenced as strongly as I was hoping it would be. It's also possible that that won't have any effect on it at all. But we'll see. That's part of this experimentation process. But the spikes that we see there are very narrow. Let's see what the pulse width of those are here. Right now we're at the 20 microseconds per division. So if I expand that out, there's one of the pulse widths right there, if you can see it. And of course it's not the same every time around, so we see a lot of jittering or oscillating around between each thing. So I'm not sure what the reason for that is, but some variation in the signal. So let's see, the pulse width. What do we want to take a look at that width here? It's quite narrow. This now is at the 1 microsecond per division, and that looks like it's about half of. If you look at it right between my 2 fingertips, right, the very tip of that pulse, it's about a half a microsecond in width. But of course, if we measure it all the way on down to its beginning, down here, it's of course much wider. But it's a pretty narrow pulse, relatively speaking. It's around a microsecond or so altogether, 2 at the very most. And the frequency between pulses, if we look at the negative pulse there, that's 1, 2, 3. We're going to say 4 divisions at the 2 microsecond division scale. So there we have 8 microseconds between a cycle, up and down, negative and positive. But then the cycle doesn't repeat, which would be the frequency, until out here. And now we're down to the 20 microsecond per division again. And this should, I dropped it down to 50 microseconds per division, and we should see about 3. It's a little less than 3, but it's down close to the 7,800 hertz. Maybe it might be a little faster than that, 8,000 hertz or so. But it's just a little bit less than 3 divisions on the 50 microsecond per division scale, which would be about, I can be a little more accurate than that. Let's say 1, 2.5, let's say 2.5 divisions. So that's 75 microseconds. No, I'm sorry, 125 microseconds. That's 125 microseconds for a complete cycle. That would be the frequency that we're going in there with. So you can figure out what that is. Take the reciprocal of it to get the frequency. And but as you can see, 2 volt per division, we got 2, 4.5, and so that's about 9 divisions altogether times 2. So that's 1.8 volts. Actually, I'm sorry, that's more than that. 2, 4, 6, 8, 10, 12 to 14, something like that, in that range. So at any rate, we're not really generating enough gas to be useful yet, and we have been able to get the MC12 circuit to drive the thing at the frequency we need. We probably need some impedance matching or some other things to be fixed as far as the driving stage of that's concerned. I do have several different MOSFETs that I can try. I have a 46 amp and 100 volt MOSFET that I can put in there and see if that works any better. and I'm just not that proficient with MOSFET circuitry. I'm familiar with it, but I just haven't designed with it very much. So they're voltage operated devices as opposed to current devices, which are bipolar devices or current mode devices. But again, we don't have as much experience with MOSFETs as we do with bipolar designs, and so there could be some biasing or some issues there that would help us to drive that coil a little better. And if any of you have any comments or suggestions about that, I'd sure appreciate it. Meanwhile, I'll pour over my my archive of schematics and circuits that I have collected over the years and see if I can find something that might be more appropriate to a low impedance inductive load, and see if that helps us out. So at any rate, that pretty much concludes the testing that I wanted to do today, I think. And I was going to determine whether or not the changing of the yeah, I've forgotten it again already. I had figured it out when I had turned the camera off, but I've forgotten what it is. There was one other characteristics I was going to measure that dealt with the loading of that MC12 circuit, but it's really not that important anyway. So I think that'll do it for now. Thanks again for watching. I sure appreciate it. Take care.